Hey, physics kids, online kids, how y'all doing? It's Mr. Goya coming at you. I'm wearing my hat cam, and hopefully you can kind of see what's going on. I'm kind of in my room here. Let me show you around here. I hope you all doing okay. So today I wanted to present some notes over work, energy, and power. And I don't really have any skeleton notes for you, but you can sure kind of get them off of here. Now, what have we really dealt with so far? Well, we've dealt with then basically the three types of energy that we often see in physics. We're talking about kinetic energy, we're talking about gravitational potential energy, and we're talking about dissipative, or, boy, can I spell that? Dissipative. Well, I'm sorry if I misspelled that. Dissipative energy. And this would be like energy of friction or heat energy, etc. Now, it's these two that really are going to concern us the most because we can kind of quantify those. We said our kinetic energy was energy of motion, right? And I'll just write that in, energy of motion. So any object that's moving will have that type of energy, and that's 1/2 mv squared. Okay, we'll put the mass in kilos, and the velocity then will be in meters per second. Hey, don't forget, we got to square that there, okay? And when we take that then times 1/2 mv squared, we get then a KE that basically is the amount in joules. So energy then is measured in joules. Now GPE then is energy of position. So we're talking about a height above like a ground or a reference point. So your ground is kind of considered h equals 0. And we're above that in some amount. And basically the idea is this GPE, we saw with that skateboard, that GPE can turn, so we had that skateboard person, and there's my skateboard, and as the person goes down, then this GPE is converted into kinetic energy. And then on the way back up, that kinetic energy is converted into GPE. And if we have no friction, then we can oscillate the skateboard person on that sim, just go back and forth and back and forth and back and forth. In a real ramp, we would have a little bit of friction, dissipative effects. And we would have a little bit of friction there. Can you see my notes? I'm sorry if I haven't been looking down lately. But anyway, we're going to typically sometimes ignore this dissipative energy and deal with what are called friction-free ramps, but these really are the three types of energy that are involved with kind of in high school with motion. Now, the question really becomes, what really gives objects energy in the first place? Well, for that, we've got to turn to this new concept called work. Now, work means a lot of things. There's a lot of words. There's a lot of meanings for work. Like, hey, I got to get up and teach today. I got to go to work, But in this case, we're talking about physics work. And it's really the work that then that something or someone can do for an object that will give it kinetic energy or potential energy. So the work really provides the energy to an object. Well, so work, we've talked about Galileo, we've talked about Newton, and after these two individuals presented their concepts, their ideas, and after they passed away, then people were starting to use their ideas in kind of creative ways. And so, for example, Newton, his sort of bailiwick is the idea of forces. And Galileo talked about velocities, displacement, etc. Well, it turns out that work is a product of Galileo's idea of a force, Newton's idea of a force with then Galileo's idea of displacement. So let me give you kind of an example. Now, if you study physics a little bit more in the future, there's an equation with a little bit of trig in it that more defines this concept. But for this class, I'm going to just really make it basic, which is fine. So we would say F, a force, which again is a push or pull, times then a displacement. Well, that's xf minus x sub I. And that's going to be then our definition of work, at least for this class. Like I said, in a more advanced class, we also have to get in cosine theta, but don't worry about that for now. Well, let me kind of give you the lowdown here. So let's say we have maybe an object on a flat surface. And let's say we're dealing with a friction-free surface. We know those don't really exist, but we can imagine they exist. So I could basically provide a push here to this box. I could push or pull it, for example. And maybe I give it a force of, 100 newtons. Remember, newtons is kind of the unit of force in the metric system. And I start here, and I maybe push it, then this would be x sub f, and this would be x sub I. And I push it for maybe 5 meters. That would be my displacement. So my force, when I multiply it by my displacement, I get work. So for this, in this case, I've got 100 newtons times my 5 meters. And that's going to be 500 newtons worth of work. 500 joules. Newton meters is a joule. That's the same unit that we have for energy. So I get 500 joules worth of work. Well, what exactly does that work do? Well, as I push this object on a friction-free surface, its velocity will increase. Does that kind of make sense? That would be Newton's second law, F equals ma. If this is the only force, if I have no friction, this is the only force pushing the box forward, then it's going to get faster and faster. Well, as it gets faster and faster, then its kinetic energy is going up and up and up and up. Right? Does that make sense? As velocity goes up, then its kinetic energy is going to go up. Well, so that 500 joules worth of work goes into the kinetic energy of the object, 1/2 mv squared. So this work can be, we're doing horizontal work, and we're giving that object then kinetic energy. So then at the end of this 5 meters, I basically have given this object 500 joules worth of energy from that work that I did on it. Now, in a real world, we would have some friction. And some of my friction would involve then, or some of my energy and work I do will go into dissipative energy. But because I'm dealing with a friction-free surface, I don't really have to worry kind of about that in this example problem. And in fact, if you study physics at a more advanced level, then you can deal with it then. But again, this is just kind of a basic introductory course. Okay, but does that kind of make sense? That what I do here, okay, if I give this an unbalanced force, going back to Newton, unbalanced forces cause objects to accelerate. And that's what we're seeing here. My velocity is going up and up and up and up. If I only push this like 1 meter, it wouldn't be going as fast as if I pushed it 5 meters. So this work goes to kinetic energy. Well, let me give you kind of an example here too. Let me give you maybe another example. Let me get another sheet here. So let's say maybe we've got somebody pushing on the box at 200 newtons. So there's my force. And let's say we move the box, I guess I should have started it here. We move the box 10 meters. All right, that would be x sub f minus x sub I. So there's my displacement, there's my force. So the work, force, again, times the displacement. 200 newtons times 10 meters, or that's going to be 2,000 joules. Now again, at a more advanced level, we can talk about, lots of forces on the object. We can get a little trig involved if we have so in a more advanced class, we might have a force at an angle. And we have to use then cosine theta to kind of help us, or sine theta, etc. But don't worry about that for this class, okay? But if you explore these ideas, if you explore the idea of work on the internet or on YouTube, you'll see a more complete equation for this. And we don't need to really worry about that for this class. Okay, do you need to do another example maybe? So we could maybe push on something at 100 newtons. And maybe I go for 4 meters. 100 times my displacement is 400 joules. What did I get from this? Well, this object's going to get faster and faster and faster. Its kinetic energy is going up and up and up and up. Okay? So by the end of that 4 meters, I've given the object 400 joules worth of kinetic energy. Okay, so my work can give the object kinetic energy. So that would be like horizontal work. So horizontal work, kinetic energy. Sorry, I'm a little bouncing back and forth here. Kind of hard to keep my head still. Well, we can also do vertical work. So maybe I'm lifting this box. I'm not very good at drawing, but maybe I'm lifting this box vertically upward. Well, it's the same really idea. I have to supply a force. And so really, this force is going to be the weight of the box. I have to lift the weight of the box. And I have to lift it upward. So again, the ground is considered the baseline, height equals 0. But now I'm going to lift it a certain displacement. Now we kind of call this YF and YI, since I'm dealing with vertical motion. So I have to lift the weight of the box, or I have to supply a force that's upward, and I have to do that over the course of a displacement. Same idea, really. But now what I'm going to give the object, vertical work gives the object then GPE. Gravitational potential energy. Does that make sense? So as you go up above the floor, or the reference line, we give the object GPE. And I can do that. Just like here, I can push the box horizontally, right? And I give it kinetic energy. Here I can lift the box, and I'm going to lift it maybe to a certain height, and then I'll just hold it there. So let's maybe, here's a like example. Let's say I'm actually doing some weightlifting here. All right. And maybe these barbells is 100 pounds. Well, let's put it in newtons, since we need to put it in newtons. So let's say we got 100 newton. That'd be the weight of the barbell. So I have to apply a force that's equal to that weight. There's my force. And maybe I lift the barbell from the ground, so YI would be 0, or H is 0. And I lift it up, I don't know, maybe 2 meters. So the height of the barbell is now 2 meters. That's my displacement. So I get the barbell up like that, and now it's at now I've given it maximum GPE for that height. So we could say, well, my GPE is going to be equal to my vertical work. But that vertical work is just the force, the weight of the barbell, 100 newtons. Okay, force times then my displacement. But now it's really, yeah, I could say YF minus YI. And that'll be my vertical work. Okay, so I'd have 100 newtons times my 2 meters. Or I've done 200 joules worth of work on the barbell, and now it has 200 joules worth of GPE. Now, if the barbell comes down, it's going to change that GPE into like kinetic energy. Okay? Let's maybe do another example. So maybe I lift this box over my head. Maybe this box, I don't know, has a weight of 200 newtons. And I lift it maybe, I don't know, 1.5 meters. I'm just thinking of my height. So I might say, well, how much GPE does this box have? Question mark. Well, that's going to be the vertical work. So there's my force, and there's my displacement. So my work I do, W, is 200 newtons times 1.5 meters. That's going to be 300 joules. So how much gravitational potential energy does the object have? 300 joules. That equals the GPE. Now notice, if I don't lift it as high, my GPE is less. If I lift it higher, it's going to be more. Just like with our skateboard person, right? When the skateboard person was down here, there's less GPE. When the skateboard person's up higher above the ground, there's more GPE. That all kind of makes sense. Let me zoom out here so you can kind of see the whole picture. Again, at a more advanced level, we can get other forces involved. We can get some angles involved, etc. Okay, but we don't need to do that right now. Now, there's one other concept that's not really hard to explain, and it is something you should know a little bit about. Power. Power is a rate that work or energy is done. Okay? A math teacher, whenever you see that word rate, that means something's over time. In this case, it's going to be work or energy over time. Okay, does that kind of make sense? Let me give you a couple of examples here. So let's go back to pushing this box. Maybe 5 meters. X sub F, X sub I. So let me put my force in here. Let's just make this really easy. 100 newtons. Okay, so by the end of the 5 meters, okay, so our kinetic energy is going up and up and up. Okay, because our velocity is going up. So at the end of the 5 meters, you might say, well, how much kinetic energy have I done? Well, that's the same as the work. So in this case, horizontal work, I've got 100 newtons times 5 meters. That'd be 500 joules. So the work involved, or the kinetic energy that the object, this box, has is 500 joules. Now here's the thing with power. We want to try to figure out, or we really need another concept, because we want to talk now about time. Like, how much time did it take for me to do this? So let's say there's 2 people involved. I'm going to talk about my brother here. I've got a twin brother. I didn't know if you knew that, but my brother is Mike. My name is Alan. So we can both push on the box with the same value of force. And we can both push on it. We can both push on it 5 meters. So Mike does 500 joules worth of work. I do 500 joules worth of work. We both do the same amount of work, and the object, the box, has the same amount of kinetic energy at the end of that 5 meters. Okay, does that make sense? Now, however, my brother, it might take him 2 seconds to move the box, and it might take me 4 seconds. So see, the work and the energy is the same, but the power is not. So the power for Mike, so Mike's power, that would be the number of joules. Okay, the work or energy, the number of joules over the time. Again, the time has to be in seconds. So Mike does 250 joules over seconds. Well, it turns out that these units, then those units are called the watt. So Mike does 250 watts of power. It's a rate that work or energy is done. My power is the same work, but now I have to put it over 4. So I'm 125 joules per second, or watts. Watts! What? Watts of power. Okay? So my brother is more powerful than I am. He's twice as powerful here. Now, you might know a little bit about watts because we measure the power of light bulbs in watts. We might have a 100-watt light bulb. You know, we might have a 100-watt light bulb, or, you know, that are, 100-watt light bulb is brighter than maybe a 60-watt light bulb, right? Okay. Well, this is consuming 100 joules worth of electrical energy in 1 second. This is only consuming 60. So this is consuming more energy. It's brighter. But it also costs you more electrical cost to run that bulb. All right? Well, let's do a vertical example. I know this video is getting long, and let's kind of get done with it. So here's my barbell. Okay, so we got my brother and we got me. Okay, so this is Mike, my brother, and this is me. So maybe the weight of the barbell, in both cases, it's, well, I don't know, maybe 300 newtons. I'm just throwing out a number. So the barbells are the same. And maybe both of us, we're both about the same height, so maybe we're both lifting that barbell 2 meters. So 300, so that's my force. Let me get my computer back on. There we go. 300, that's my force, times my displacement, 2 meters. So 600 joules worth of work, or GPE, that the barbell has. Same. 300 times 2. Maybe my brother can do this in 1 second, and maybe it takes me 2 seconds. So again, that'd be time. So the power of my brother would be 600 joules over 1 second, or 600 watts. My power is 600 joules over 2 seconds, or 300 watts. My brother is more powerful than I am. We can do the same amount of work, but he can do it faster. Now, do you understand when we have something in the denominator, okay, time, so this is power. When time's in the denominator, if time is high or large, then power is low, is smaller. When time is low or small, when I have a small amount of time, my power is going to be larger because of that denominator. Okay? So what all have we talked about? Ooh, look at all the pages. I've got a lot of pages here. Okay. Okay, so let me get back here. Okay, we talked about work, energy, power. Talked about the two types of energy, kinetic, GPE, and dissipative. The work I do is force times displacement. It can be horizontal. Okay, there's a couple of examples. It can be vertical. There's power. And there's another example. Alrighty. Well, I think I've made this video long enough, but I hope that kind of makes sense. We'll talk to you later, kids. Keep working hard.